Exciting. So let's get right into this week's meeting. As a quick thing, I believe Dieter was going to give us a command line interface tour of his package. With that, we can run through the quick reports and then move on to that afterwards. Does that sound good? Okay. So see Devin is listed first on the quick reports here.
Yeah, sure. So I've just been working on finalizing the EM1D stuff. So talked to Soggy a little bit and we came to a consensus and we decided to make a waveform class, and we're just putting everything in its final place, and I'm updating the tutorials and tests. So progress is being made and I'm hoping to finish that off for a final review pretty quick. Hopefully in the next week, unless stuff gets in the way.
Is that being added to the waveform class that kind of already is there?
No, we talked about this, and there really just is no strong overlap between how the 3D and the 1D problems are being solved. And I strongly advocated to have a structure where if you import this module, you'll have all the tools that you need for that module, and you won't have other stuff. We didn't really want to combine the 1D and the 3D stuff in any way, but there is sort of like a 1D utilities package under the utilities. So does that kind of answer your question, or?
I guess I still need to look and see what's different, what's so different about the 3D and 1D waveforms. I just assume there's a time series, or there's like a general time series, or there's a they're just generally functions of time.
They're similar, I guess, in that you have a discrete waveform. I think for one, for your 3D problem, you're going to be discretizing things based on the time stepping that you've chosen. Whereas for the 1D stuff, you're going to be putting something in, and then it's actually going to discretize it according to the times it needs to do the convolution. And I guess I didn't like the idea of creating classes that you could use for the 1D problem and you could use for the 3D problem, but it just had the properties of everything. Because then it might not be as obvious which properties are being called for the 3D and which are being called for the 1D. I guess I didn't see like the obsession with trying to just make a singular waveform class that would work with everything. I thought it'd be nice if you just put the 1D stuff and the 3D stuff in separate places and created more kind of simulation specific lightweight classes.
I'll still have to go through and look at it again, but I could also imagine like those kind of parameters being set by the simulation itself.
Yeah, I mean, there was sort of a desire to, I guess, make the interface between the 1D and the 3D simulation to be similar, right? That like if you were to go through, say, a forward simulation script for 1D and 3D, the steps would always be the same. I thought there was a desire to kind of keep the user doing things in a very similar linear way.
Yeah, I'll just need to look at it more myself, I think.
Okay.
So Devin, can you just kind of explain what is different here with the 1D versus the 3D and why it becomes so convoluted to have them all together?
I guess if you were to go into a part of SimPEG and it was called time domain, and you had all the functionality of the 1D problem and the 3D problem sitting in that area, you might not intuitively know what functionality and utilities are going to be used in solving a 1D problem or in solving the 3D problem. Because the 1D problem, you sort of organize it by, you sort of solve it by, for each location, you solve all the time channels. Whereas in the 3D problem, you'd be doing the time stepping and then projecting it to all of the receiver locations. Like it's kind of the opposite in a way.
So my thinking though is that that seems like things that could be handled by the internal mechanics of the simulation. Like that difference right there could just be handled internally to the simulation.
That's true. I mean, I guess let me ask you this question then. Do you want a receiver class that is used for both the 1D and the 3D problems, where you, let's say I'm doing the 1D problem and I'm looking at sort of the attributes or the properties of my receiver. Do I want a bunch of stuff like a projection matrix or a bunch of the heavy stuff that would be used for the 3D problem? And my answer to that is no. I'd like to be able to just see the stuff relevant to the problem that I'm working on.
Right, I understand. The thing is, like, you don't have to use all those projection matrices.
That's
like
true.
If all you want from the receiver is like its location and its time, that's all you need to ask for.
Yeah, but when you're looking through and you have an object and you're working in on some kind of problem, wouldn't you like to just have access to the stuff relevant to that problem? Because then you're rooting through and you have all these objects or all this functionality that you can call, this really long list, and as a new user you don't know what stuff is supposed to be called or used for the 3D simulation or what stuff is for the 1D simulation. I just think it's really confusing to have this heavy class that you would be using for all of these different simulation types. Because if I want to learn about what this object can do, what methods are associated with it, I'd like to be able to work in sort of the space that's relevant to the problem I'm trying to solve, as opposed to making a source class, a receiver class, a waveform class that's trying to be applicable to every type of, say, frequency domain simulation.
But if you're okay, so if you're a user, and let's suppose you've got a 3D data set, and ultimately you're wanting to do 3D. But if at partway through, perhaps at the beginning, you want to just do 1D inversions, or you want to do somehow stuff that's connected with 1D. Does what you're proposing as far as splitting, does that hinder that thought process?
No, I mean, maybe I'll just, things are a little bit disorganized for me here, but I can maybe show you kind of how it's partitioned. I won't do anything that's going to take a long time, but I'll just show you kind of the biggest partition of this here. So everyone can see my screen?
Yep.
So basically, under SimPEG electromagnetics, you'd have one folder that would have the 3D simulation, and then you'd have one area where it would be the 1D simulation. So if you want to go and solve a problem in 1D, you just import SimPEG electromagnetics frequency domain 1D, and everything in there is going to be relevant to our 1D method of solving the problem. And if you want to do a discretization on a 3D mesh or on a SIL mesh, you would use the stuff inside of here. It just seemed like the most logical way to, I guess, keep the code clean and to have objects whose properties are only relevant to the simulation you're choosing to use, and doesn't have lots of kind of irrelevant properties that you're not going to be using.
One comment that I have is like I sort of understand why Joe is asking for like consistent sort of structure, and at the end, it's actually that's way to go, I think. But it's a sort of like we need the incremental steps to go there, because the current like it's quite different like how that the current PDE solver solves a problem and the 1D code solves, like it's quite different. So there are details that like I need to serve those purposes. For instance, time stepping. Like it's sort of like almost an art. Like okay, how to set the time step in the PDE code. It's still in question. How do we really handle that? Like it's even a research question. So whereas in the 1D code, it's pretty robust because it doesn't really matter how you set the time steps, but still like it costs. Like if you put a lot of time step, it still costs in 1D. So like what I would suggest, like we can sort of make an incremental step with what kind of, as Devin suggested, we have a separate things. But as we getting kind of developing our PD code more, we can sort of like go into a direction that we can merge things. At the end, like we can have a sort of common class that can handle both. Yeah, just like that would be my suggestion.
Yeah. Well, I mean, in the way that you go in and define sources and receivers, their locations, assigning things a waveform, those are on the surface, those are handled exactly the same way. So for the end user, they don't really see any difference between it, but it's sort of partitioned in I feel in a much cleaner way.
Is there a way that we could, I don't know if this is possible, but is there a way that we could have kind of one class like Joe's talking about that kind of covers everything? But then when you're actually using it, and like Devin says, if you were creating like a 1D simulation, if when you then go to tab complete for the 1D simulation to find out all the methods associated with it, that it only shows you the 1D ones, but not all of them related to the full class. Because if we could do that, we could have one single class that kind of still has everything in it, and we wouldn't have like a lot of replication in code that's been kind of copied and pasted to different areas with just like small tweaks in it. Because I can see how that would be, that just makes it harder to kind of manage the package, right? Like if you have to go in and refactor something or make a change, instead of making it in one place now, if you have like 3 copies of like the same code with kind of different flavors added to it for the different dimensions, I can see how that becomes a bigger job. But
yeah, I guess maybe the biggest reason I did it this way is for the 3D problem, if you're in the frequency domain, the frequency is a property of the source, I believe. So when you say I have this source and it's operating at this frequency, the frequency is a property of the source object, and you're going to solve a forward problem for every frequency. When you look at the 1D case, the source just has its location, and the frequencies that you're solving the problem are actually a property of the receiver class.
Why?
That was the most efficient way to solve the 1D problem. So in 1D, you say, okay, here's my source location, here's my receiver location, solve it at these sets of frequencies. So you could think about the 3D problem, the actual data vector being output by it in 3D is organized by source, then by, like, I guess, source, location, no, frequency, source location, receiver location. And then in 1D, it ends up being source location, receiver, and then frequency, which maybe we do want to change in the future. That's just the most efficient way to solve it. That's like, that's what we're doing right now.
That part
personally
doesn't
be different.
yeah, it doesn't really matter that because like in 1D, like that each computation costs. So like the order doesn't really matter. I think it's probably what I chose at one point, and I'm happy to change. So it's like it doesn't really matter that order in terms of efficiency.
In my opinion, I think it'd make more sense to keep it the way it is in SimPEG and match that. I mean, if it's more efficient to do it like the other way around, then do a sweep on the simulation to figure out what frequencies you need to simulate.
Yeah, because I feel like we had this conversation several months ago, and then we decided whatever we had now was fine, and now we're coming back and deciding it's not fine.
No, I think that's sort of my point. I think both codes need some upgrade. I think because the 3D code is not perfect, and it actually I think it's needed a lot of work to make it kind of actually usable in like a decent sized problem. So my point was like, oh, we actually had needed a lot of work to do on 3D code. So at this point, let's make an incremental step of putting like bringing 1D code into SimPEG main branch. We're going to leave it separate. And then as we go, we can actually like slowly merge things in and figure out like how we can structure the consistent survey class or simulation.
Yeah.
class.
Yeah, I would support that, because otherwise we're just in sort of a perpetual state of development, and we're not bringing new tools to people. So I would like that idea, Sagi, if we finished things up the way they are now, but definitely if it can be improved in the future, we should do it.
I would just say that my opinion is that I think it should go to where we think it will end up living in the end. Because if not, then it gets harder for people to update code. And if it's changing locations, it's a pain. I think that it should be like if we wanted to match the 3D structure, like the 3D source things eventually, like this, the source receiver, however we want them to match eventually, we should just make it match now and worry about efficiency later. But it should, I personally wouldn't want to have to keep updating my code every time, like, oh, the simulation MT or the simulation 1D EM stuff got moved around again. Oh, I got to change my code up again. That's kind of what I want to avoid.
Yeah.
Like, I don't care about the internal stuff. I just want to make sure that it's like externally not going to change, at least not very much.
I guess, is it going to be, is that going to be prioritized over the current list of stuff that we have and sort of be done in a timely manner? Because I mean, then we talk about what we're going to do with the 1D, then we also think, oh, well, okay, well, we have a 1D DC IP simulation, and then, which I think is a bit more merged together. And then we also have 1D MT stuff. Kind of snowballs into like a bigger kind of handling and organization of 1D versus 3D simulations.
One analog I would just add, because we've already sort of dealt with this structure in the 2D case. I appreciate that there's some differences there, but the way that the DC code base is structured is we do kind of have, we've got a bit of a structure to work with multiple different dimensions of simulations. And so my 2 cents would be to kind of take a look at that and try not to introduce a new sort of mental model or a completely distinct structure between the EM and the DC and also the MT. We've also kind of got a structure for 1D, 2D, and 3D. So that's just what I would add to that, to kind of echo Joe's comments of trying not to move, even if the organization isn't perfect off the bat, trying not to have that be moving around too dynamically.
Those are just like, I'm not sure if we need to come to a consensus at the second. We should have more of this discussion on the pull request. So let's move some of this discussion to there so we can actually document it and make a final decision there.
Sure, yeah.
Let's move on to the next quick report item. I see Dom is listed next.
Yeah, so this last week, John and I have been running a large DC just to test the parallelization. Seems to hold up pretty nicely, and then got a request pretty recently to start looking into parallelizing the MT, the natural source code. So that's what I'm on now. Because of your great work, Joe, it's going to be very straightforward because it's basically the exact same thing as the airborne AFM. So it's just a matter of double checking things at this point, but that's what I'll be doing this week. And yeah, if one thing you can look at is that the frequency example that Devin had written, sorry, in the tutorial part. So the the natural source simulation branch, this forward simulation doesn't output the same as before. So it would have to be looked at. I'm not sure what happened under the hood, what kind of changes happened for the FEM, but if Joe, you have the time to look into it, that'd be great.
Yeah, I'll check that out just to double check. It's a subtle change on the inside, but it could have an impact on looking at the fields from them.
Okay, yeah. So basically, if you run Devin's tutorial 3D forward, you should be a bullseye, right? And right now the target seems to be sort of on the side, or I'm not sure what's happening. So just double check that, and then we should be good to go. Because I did the merge, I already did natural source merge onto the tiled simulation, because I'm guessing natural source is going to go in first, and I wanted to start testing. So yeah, that worked. It was pretty easy, and then that's it for me.
Cool. John, what do you got? Anything to add on to that? I can't hear you, John. It says you're unmuted, but we can't hear you.
Can you hear me now?
Yep.
Is that better? Oh, okay. Yeah, I guess that doesn't work. Okay. Yeah, just pretty much I'm working at the same thing you're probably talking about, Dom. Yeah, it's when you do the test on the cross gradients, it's the real component. It seems to be giving out just slightly different values when you do the dpred for that calculation. But then yeah, I started looking and pulling out the fields, and the fields do look differently from what we had in master. But when you actually do it, it seems to work most of the time. It's just like this, yeah, I don't know, there's just something there that's just, like you said, it's just subtle. It must be some kind of subtle change that's switching things up.
But for the like the tutorial example, like the data looks nothing like it was before. So there's something pretty fundamental, I think, that's happening that we're not doing the same as before. Yeah, maybe that's a good entry point. If you can reproduce that tutorial data, then we're on the right path, right?
Yeah, I'll go down that road there this week, slowly picking away at it. And yeah, I did some tiling inversion on some cluster nodes, and yeah, ZAR seems to be staying on the node. So things are looking good. That's all I got.
I have a few quick reports on updates on the 2D MT stuff. I've been able to go through and get the formulation working correctly with the boundary conditions for all the formulations for the TM modes, both of them. It works pretty well, actually. Like it it's pretty accurate as far as the solution, at least for our half space, even near even near the edges, with just a simple. So right now I just had a Dirichlet condition at the top, and I'm using 0 Neumann on all the other boundaries, and it works pretty well to solve the 1D problem, like the 1D model in a 2D case. So it seems nice, but there's also the machinery in there if we wanted to hook up and use Dirichlet conditions on the sides as well. I'm not sure if it's quite necessary to improve the accuracy or if it would have that much effect on the accuracy, but even at this point, it seems it has a really good solution at the surface. Like it's only off by maybe, I don't know, 0.1% with that discretion, with that discrete values we were using, or that mesh that you had before. Even at the edges, like it just goes right up to the left and right sides. It's nice like that.
Tried it?
However,
Oh, sorry, Joe. I was just going to ask if you've tried a quarter space solution with the 2D yet.
I did. I tried to quarter space. It looks like it looks like it does the proper thing when it crosses over. The edge, like the sides, are not as perfect anymore. But I'll try it with the quarter space and see how it works with that, and putting the actual solution, like the 1D solutions on the side, make it have any improvement.
Were you have
So
to
what
do
is-
something for TM mode? I thought the T is kind of fine for Neumann, but TM, because it crosses the electrical field is crossing the boundary in that case. So I thought when I was reading a couple other papers, authors had to do something on the boundary for TM mode. But yeah, just curious what you had to do.
So the point is that we're saying that with the Neumann, right, that the electrical field doesn't change at the boundary. Like it's just a constant at the boundary.
Right.
But that will get fouled up if you have topography.
Mm-hmm. Like there's other rooms for boundary conditions in there, like especially with the 1D as well. The machinery is in there to hook all that up.
But are you talking about the boundary condition at the Earth-air interface?
Just at the left, maybe like the left and right side of the models. The one that we're concerned about. At the top, it's a Dirichlet condition at the top where we're just putting in ones at the top of it.
Good.
The formulation I have is I say it's technically correct. However, meaning it results in the correct A matrix, like the correct solution matrix, but the way it gets to it internally is not quite theoretically mimics the theory, because it's using right now like the phase divergence and the phase divergence operator to do it in 2D, whereas it should use like the edge curl in 2D, which does the edge curl to the faces, because we still have to take account all those cross derivatives and like the cross product derivatives. It still ends up with the same A matrix because things get shuffled around and then unshuffled. So it's the same A matrix, but it's like not theoretically the same exact, like it doesn't look the same as it should. If you would go and drive it by theory and then coded it up with like edge curls. So I was working on getting those boundary conditions working with the edge curl matrices and double checking it against the boundary conditions on the phase divergence. Something else. Oh, and then I'm also working and hooking up the 1D receiver objects and 2D receiver objects to make sure that they're working properly with the MT. So things like making sure that the impedances and parent apparent resistivities phases are calculated similarly to how they are in the 3D on the receivers, and not in like, I don't think they should be fields, like they shouldn't be part of the fields object, they should be on the receivers. And the receiver is the one that calculates the impedances and does all the transformations, right? So I'm working on hooking that up and getting that back to mimic the 3D receivers. Does anyone else have any quick reports before we go on to Dieter with his command line interface tour? Seeing no objections, to take it away then, Dieter.
Yes, I can do. I can try. Let me see. Can you see that?
Yep.
So that's not command line. I can see that, but the command line itself is kind of boring because you're just going to see 2-3 commands. So I thought I'd quick run you through the notebook, how we would run it in a notebook, and then also I show the equivalent what you can do now in the command line, if that makes sense. Just that you get a handle on how I run things. So I think everybody that is here maybe knows EMG3D. Just if SimPEG is this big thing with gravity and magnetics and EM and DC, then there's EMG3D is a tiny fraction of that. It is mostly a solver, so what you usually use Paradiso for controlled source EM in the frequency domain. So it's a very specific solver, and it uses the multigrid method to be a bit lightweight on memory and runtime in a way. And we use that in the current consortium work. It's used in the GIF, that's called the Joint Inversion Framework, where we try to currently combine NIP tomography, gravity, lab data, well data, and CSEM. And this particular case is in the Barents Sea. It's about a region with a lot of salt domes that we try to improve the knowledge of this area. So many things are similar that, like in SimPEG with surveys and simulation and all that. It's not the same for the main reason that I can often things write much simpler because I just have one method. So I don't have to take care of all the possibilities you guys have to take care of, because I just have one type of source. It's an electric source, and there is just the electric receiver, so I can simplify many things. But as you know, I use discretize, so you know this. So what we usually would do is we load a model, an H5 or a JSON or an NPZ file that has, in this case, a mesh and the corresponding model. So this mesh has 140,000 cells. That would be the inversion model. That's the current state of the inversion, let's say. We can here see the model. It's on the model is defined on log 10 conductivities, isotropic, and it has 100 by 94 by 15 cells. Then similarly, we load a survey that I use here, X-array under the hood to store this survey. So we see here my data set, the raw data has 4 frequencies, 374 receivers, 14 sources. That's actually the other way around. We use reciprocity. So there were 14 receivers on the seafloor, and then the source is flying over it, and you bin it, and this gives you 374 source signature, let's say. We can have a look at this. Well, this is the full data. Let's go to a smaller data set. I select here just a few sources to make it smaller, to run faster, and I just choose 2 frequencies. And you can look at this. So we have this named 46810 source. We have a whole bunch of receivers from 0 to 373, and these 2 frequency, and then the noise floor and the relative error. That's just how you define it. It's here a frequency dependent noise floor. So there's 2 to the power of -14 for the 1 Hertz and 2 to the power of -15 for the 4 Hertz data. And then the noise floor and the relative error, that's just how you define it. It's here a frequency dependent noise floor. So there's 2 to the power of -14 for the 1 Hertz and 2 to the power of -15 for the 4 Hertz data. 2 to the power of -15 for the Then you can plot this so you have an idea of what the model we have. So this is again on log 10 conductivity. So you have here these big salt domes. Let me see. It's relatively shallow. It's something above 200-meter water. So you have still a huge influence of the air layer. We have here these 4 sources and then this receiver line that goes over these salt domes. And then similar as in SimPEG, we define with that a simulation. A simulation takes a survey, a mesh, a model, and then it takes gridding options. So under the hood, it will create automatically a computational mesh because this input mesh here, that's the current inversion model, is not wide enough. Particularly the air has to go much higher and the boundaries, but it does that internally. You can also define how many parallel processes you want to run. I put here 10, I run it on the server, and then you can compute the forward model, and we don't wait for that, but that's the example. We have here these 4 source location. We have the receivers. The colored curves here are the measured data, which we probably have to cut a bit more. We didn't do a lot yet here. And then the gray lines behind are the synthetic data we computed. And you can also do the gradient for that. And then save it to an H5 file. So that's how you would do it in a notebook. But we said we're going to do it on the terminal. So let me make that a bit visible. Is that visible?
Mhm.
So now when you install EMG3D, just as you usually do with pip or with Conda, then you get a command line tool that has a lag, which seems to be a common problem, which is a bit annoying to show it, but if you run inversions, it doesn't really matter. So this is your command line tool. So you can define your number of processes. You can, it has at the moment 3 functionalities. By default, it just does the forward model. If you have data in your survey, you can get out the misfit, or you can ask for the gradient of the objective function. You can, in the terminal, define where you have your survey model or output file and the verbosity, or it's mainly driven by a configuration file. So this is such a configuration file. You can define here the names of your survey, of your model. You can put in simulation parameters, like if you want to have a single gridding for all data, or if you want to have source-specific gridding, how many workers, solver options, like you do it for, like you can do it for Partiso, the gridding options, and you can also do data selection. And then we can do it has a -D flag for dry test run, so you can look if it can find all files and it can write the files, so you don't run a whole modeling and then just to find out it fails because it couldn't write the file. And then you can see it loads the survey and the model. It creates a simulation, and then here will come the forward because we did the dry run. It doesn't do the forward, and then it saves the result to your defined things. And if we take here the dry out and we actually run it, then again, it will read the data, it will it will take the survey, it will take the data you selected, and then it creates the internal computational meshes, and now it does the forward computation, and at the end, it will write it to your file, and that's how, at the moment, runs this joint inversion framework with the partner companies. So that was it, very brief. I thought I'd make it quick, and then you have time to ask questions, and I can explain more if there are.
What does so say I set the 10 processor, what does it do for your code, Peter?
It just uses the Python concurrent futures. So it just throws them off. It puts them in a queue of the concurrent futures, and it runs it on 10 threads, I think. Or what do you mean? So they are then completely independent.
Right. Like I was did you parallelize your code? Like, is it gonna separate your different frequencies, or like, I was just kind
Yes.
of curious.
Yes. Sorry. Yeah. It can only run in parallel. It does it for frequencies and for sources, because it has to do that. As it is an iterative solver, it has to model each source independently. There is no other, well, yeah, the way it is implemented. So each source is an own computation and each frequency is an own computation. So the parallelization is simply over sources and frequencies.
Right.
Yeah. It is.
Oh, that's very nice.
Yeah, it would be.
Impressed.
I guess there are possibilities to parallelize it, but because it's iterative, so it goes from one node to the other, you would have to start to do very clever things to not mess up your solving capabilities.
I mean, the frequency and source is already pretty good, I guess. Like, if you can parallelize that,
Yes, and you saw here that was a mesh. The computational mesh was here, well, 560,000 cells, so not massive, but it took each like between 50 seconds and a minute.
That's good.
And then it comes back, so yeah.
When you
Yeah.
when you do the solver, are you starting from scratch each time, or do you make any use of previous computations from a nearby transmitter or something?
So that's a good point. Here, when I throw it away, well, when I put it out in parallel, then it starts from scratch each time. I did some testing with when I did time domain modeling, and I needed a lot of frequencies. If you go from one to the other frequencies and you use the previous frequency as a starting point, it can speed up, but it can also slow down. It can be beneficial in low frequencies because it doesn't change a lot. But then when it comes to the region where it becomes highly oscillatory, you might even start at a worse point than by starting with a zero field. So it's at the beginning I tried a lot, and then at some point I just settled with I just start from scratch. Yeah. But it would be an interesting project to see the conversions. But it's funny because when I really went at the beginning into this multi-grid solver, there are so many different things, like how do you loop through in a W, in an F, how many pre-smoothing and post-smoothing step do you use, line relaxation, semi-coursing tricks to make it faster, and everything works in some cases, in some others not. And in the end, I see most people I know, then they just settle with maybe a slow version, but a robust one, because it costs you more time to try each time which one would be the fastest one than just use a slower but stable one and just let it compute in the background.
Yeah.
But I guess if you would start a large project and you know you're gonna run hundreds of inversion, then it would be a parameter test would definitely be something worth doing it. Yeah.
Are you like using that as a preconditioner, Dieter? Like your multi-grid is a preconditioner, and you have a separate iterative solver to solve actual like a simulation? Is that what you're doing?
It can do both. You can put into the solver, you can either use it as a solver on its own, or you can do one multi-grid step, and then you can choose any of the SciPy Krylov subspace solver, like big conjugate gradient stabilized or conjugate gradient or any of those, and then go back to, yeah, as a preconditioner. So yeah, it's both in there. It uses more memory. As soon as you then use a Krylov subspace solver, it will use more memory. The cheapest is if you only use the multigrid, if you have huge models.
Yeah,
See here, does your implementation automatically do the receiver source reciprocity to reduce the number of sources?
You mean within the code?
Yeah, within the code, or is it something that the user has to do for it?
Yes, at the moment still, it's still you have to define the survey in such a way. Yep. That's actually something I would like to do, but then you have to think again how you save it. Can SimPEG do it? If, then I can look what you do and avoid the thinking about it.
There's a little bit of that thought in the DC problem, but not, it somewhat translates to that problem as well. I mean, it's just kind of like, okay, well, let's count. At some point, like the crudest way is just like, let's count the number of receivers and then the number of sources and do whichever one's smaller, right? That's like the crudest way of doing it. But
yeah, it's at the moment, the thing is, the way you have it implemented, the source can be arbitrary shapes. You can even make a loop and then you have a magnetic source. You can make some line source, finite length source. And receivers, as they are implemented at the moment, are just point dipoles. So it's an interpolate. You interpolate it at one point in your space, right, and get the field there. So you would have to do that by hand. So it's not as easy as just flip it around, because then if you have a finite length dipole source, you cannot just flip it around. Yeah.
So Dieter, if you have a magnetic receiver, then like to use the reciprocity, you need to have a magnetic source, right?
Yes.
So are you just like a discretizing like that kind of with the electric source? So you got kind of just make a loop.
I just make a 1 by 1 meter square loop perpendicular to it. Yeah. Well, I don't actually have magnetic receivers because everything is, I don't have different formulations. It's EMG3D just does electric source and you get the electric field and then you just use Lorentz to obtain the magnetic field, right? And interpolate it from there. But if I then want to back propagate the field to create the gradient, I need magnetic sources. And yes, I do that by just making this square loop, electric loops, which gives me a magnetic source in a way, a dummy source.
Got it.
So yeah, all these things, it's by default, it's an electric source, an electric receiver, and everything else needs a bit of fiddling. It works because you have the solution, right? But it needs a bit of fiddling. And yeah. But yeah, that's a command line interface. And I mean, it's much easier for EMG3D because there are only a few things you can do, I would imagine. For SimPEG, you probably would have to choose on 1 or 2 things that you want to start to have available on a command line tool. But yeah. It's mainly because these other companies, they don't really use Python. So this way it makes it easy because they're used to the command line and they have all their run scripts and their init scripts. So this way it makes it easy. You could also make it with a Python -C and then your command, but it's in the end, it's similar, yeah.
Yeah.
cool.
Yeah, and it's actually not that difficult to implement. I thought it would be worse, but Python is so mature, they have something for everything. So it's just... Yes.
Looks very professional. It's better than a Python script. It looks better than a Python script.
Just the way it looks, right? The look is everything. The cool thing is then I didn't share anymore. What it helps to me, let me share again. What is good for me when I drive and I have to, does it share? No. When they have issues with it, then it writes these log files where in the beginning, I have the usual Scooby report we have, and then it prints what it loaded, what were the parameters, what were the survey, the message, all that, it logs that file. It would print here solver errors. So if they have an issue, I can often just solve it when they send me the log file. And so that is definitely something that helps. I don't have to tell them run this command and tell me what is the output, or do that and tell me what it shows. I can just say send me the log file, and that makes things quite easier to client support. How do you call it? Yeah.
Diagnosis. Yeah. Yeah.
Yeah.
Which raises a good point for us. I was looking at the directives to save results, and we have about 4 directives that do sort of hack jobs on each one of them. It would be great if we have one directive that can, you know, with switches on it that decide save this, not this, you know, and just consolidate everything we have, because right now it's a mess.
No, I agree. And every time I look at them, I'm like, oh, it doesn't save what I want. So I end up writing my own in my notebook anyway, because it doesn't save what I wish.
Exactly. We should sit down and all agree, like those are the things that we want to save default. Those are the switches we want to add, and then just have one directive that saves saves inversion.
Cool.
There you have your next hack session.
Yeah, with that, we discussed last week, we're going to have another, you know, SimPEG afternoon coding session / social hour / whatever we want to do at some point, or on Friday, this Friday afternoon this week. We've been doing them around 4 o'clock, so I think that's still 4 o'clock Pacific time, so it should work well. Feel free to stop by if it goes past, you know, normal working hours, or we decide that we're done coding. We'll play some games or do something else.
Sounds cool. Too late for me, but sounds cool.
Yeah, with that, unless anyone has any other thing they'd like to share, I believe that's a good place to call it for this week. See you all on Friday.
See you next week, folks.
Thanks, everyone.
See you. Have a good day.
Bye.
Bye.